Before we begin the demo, let me tell you a little bit about our company, Matrickz. All my colleagues here are from Matrickz, and we work 100% in the automotive domain. We work in 4 different areas. One is ECU development. So we develop the end-to-end ECU. We work as a tier 2 company. So tier 1 companies make the system. The system consists of software, hardware, and mechanics. They provide the hardware and the mechanics, and we make the software for them. And this is what our one department. And then we have a safety, functional safety, and a SPICE department where we do safety consulting, safety concept, and that kind of activities. We have a testing department. If you're familiar with the classic V model of automotive, we're on the right side of the V model in this testing department. And finally, we have a security department. And my colleagues here are going to show you one demonstrator they have built as our penetration testing test bench. And one thing that I want to tell you, we were talking to some of you in the break, that we're looking for new colleagues in this area in security. We're looking for master thesis students or interns. If you guys are interested joining a hands-on project where you will be able to do hands-on work with real ECUs, with real cars, where you will be finding out mechanisms to break into it, this is a very interesting area to join. Please feel free to write me, get in touch with me. We'll be happy to have a talk. So without further ado, I'm giving it over to Pravin. Pravin, why don't you introduce yourself and take over the demo? Thank you.
Okay. So my name is Pravin Suvarna. So currently I'm responsible for embedded development and AUTOSAR department here at Matrickz. My entire experience is in the automotive domain. Throughout the projects, I've worked on AUTOSAR and functional safety. So in this demo, this is something really interesting for us. My colleagues are also with me who helped in this demo. I can introduce Falgun. He's the one who has set up this demo along with Klaus. He's in the back seat relaxing. And my colleague Jay, who is taking part on the hacking part, like how do you penetrate into the ECU and how do you hack messages. So before we show the demo, I would like to go through a few of the slides to give a bit of a motivation into the project. Maybe we'll start. Okay. So normally the question comes before we start into anything, why security is important in a car? I'm sure based on the previous talks from other speakers, now we have more reasons to say why security is important. Especially in the past decade, based on some of the use cases of hacking a car, the OEMs or the car companies are much more serious about the security now. And also with the autonomous driving, which is rapidly coming into the picture, security is playing more and more important. And also we have connected cars coming up. And there was also a mention about the new security standard, ISO 21434, which is also coming in 2020. So normally we currently have a standard ISO 26262 for the safety, but when it comes to security, there are no standards yet. So it could differ from project to project or companies to company. So maybe from next year we will have some definite standard for the security, where it defines each of the life cycle for the entire project, which makes maybe our life much easier. Okay, so before we go into the actual topic, let's see some of the consequences of hacking. What can go wrong with the hacking? So with the hacking, maybe an unauthorized person may be able to lock or unlock the car, or maybe he'll be able to turn on and off the car. Because it's normally a use case coming from keyless go, the ECU related to keyless go. There was hacking done by ADAC way back in 2014. So what they did was, when the car owner was sleeping in a bedroom and the key fob is with him in the bedroom or in his living room and the car is in the garage. So normally in order to open the door, it's in the PEPS, it's a passive entry, passive start. Normally in order to open the car, you need to have authentication between the car fob and the key fob and the car computer. So what they did was they came up with a device which didn't really cost more than few €100. So they did this handshaking between the key fob, which is in the bedroom or a living room, and the car, which is in the garage. So next day when you wake up, you only have a key fob, no more car. So I have also worked on a similar project for one of the German OEM for almost 2 to 3 years. So even when I see that project, the entire ECU of this keyless entry, keyless start had hardly one safety goal. The only one safety goal is whatever the message you read or the key stop, the start stop button you read, that should be safe. Other than that, what about the security bit? The authentication happening between the key fob and the car computer, there was no mention. Why there is no mention? Because there was no standard. This could be one reason, or maybe the OEM doesn't think which may be of high importance. But over a period of time, now if you see maybe 4 years back, if you see a ECU of a keyless go, and if you see a keyless go ECU now, there's a lot of difference. Maybe long back then we were using RF frequency. Now there are NFC is being used, or there are ultra wideband frequency is being used. Shortening the time, and also they have set a definite time limit. The handshake should happen between few milliseconds. Otherwise, it won't be considered as authentic. So there are many other mechanisms. But definitely, if you consider, okay, is this enough? Maybe we don't know, because there is no standard in place.
So I was talking about the Chrysler Jeep hack, which started getting into the infotainment system, because normally the car companies also say, hey, you got into the infotainment system but not into the CAN bus, so there is nothing much you can control. Because whenever this attack started, also it was normally with increasing the volume. Maybe, for example, if you are in a high speed, and if the volume is suddenly increased of the car radio or car multimedia, then it can have an effect. So normally even the companies say that, hey, there is kind of isolation between the CAN bus communication and the infotainment. If you really get into infotainment, there is nothing much you can do. But again, they improvised their hacking, and they were also able to download their own version of software through which they can get into the CAN bus system. So they could control almost, the entire car. So there are many other cases where you can modify the firmware, or you can update the remote firmware maliciously. This was also one of the second phase of the Chrysler Jeep attack, and also inject arbitrary CAN packets. So there is a lot of consequences if someone can really get into the car, or can access the car. Okay, now coming to the possibilities of hacking, there are two types. One is the wired access. You have a wired access to the car. You have access to normally the CAN bus or the OBD port of the car, wherein you can connect your ECU or hacking ECU to the OBD port, and you can try to read the CAN messages. The second one is a remote access, that is normally happens via Wi-Fi or a Bluetooth. If you are in a Bluetooth zone, then with the same frequency, or with a Wi-Fi, if you're in the same network, there are possibilities, and also with the GSM. So normally it's a wired and remote access, but in today's demo we are more concentrating on the wired access. So we're going to talk about how we can get into the CAN bus of the car, or and try to read the CAN messages, and how we can alter to show our control over the car ECU. Yeah. Okay, so now coming to the car hacking technique, there is something called autoimmune. Have you heard of this word, autoimmune? This is also one of the disease. There is a disease called autoimmune. So normally autoimmune is a disease where immune system of your body by mistakenly attacks your own body cells. So normally when it comes to hacking, what we do is the hacker of the ECU waits for a target component to send off one of the frame. For example, if you want to hack X ECU, then you wait for its frame. Your ECU will wait for its frame, and at the same instance, the hacker ECU sends its own frame by corrupting single bit that overwrites the original frame of the targeted ECU. So by doing this, what happens is whenever the target ECU identifies that, okay, there is an incorrect bit, it tries to recall the message, recall this faulty message. So over a period of time, by doing this way often, you make this target ECU feel that it is already sending a lot of faulty messages, and also it will inform the network that, okay, maybe something wrong with me, so I will disconnect. So this is one of the hacking technique where normally used not to override any functionality, rather to disable one of the functionality. So that's how it works with the autoimmune. There is another hacking technique where we modify the content of the message. So the first one is not about modifying the content of the message or overriding, but the second one is about the modifying the content of the message. So here you get into the car canvas system, maybe through a OBD port, and try to listen in all the messages, because you don't know what CRC they are using or what polynomial they are using, so you won't be able to hack that easily. So you will start listening to the messages which is being exchanged in the canvas, and once enough messages are accumulated, we start analyzing the content of the message, like, okay, what is the arbitration ID, what is the message length, what is the content of the message, what is the CRC, etc. We try to capture the data, we try to analyze the CAN messages. So in this case, we also try out different CRC polynomial functions, because we don't know, there are n number of CRC polynomial functions, and the manufacturer of the ECU or that function might be using any of them, so you don't know. So it's kind of a brute force. You have to keep trying with a different polynomial, different CRC, until you get it. And if there is try to send a new frame with some of the arbitration IDs and observe the response, because it's kind of a trial and error method, brute force. So you keep checking. Whenever it is not the right CRC or it is not the right ID, you will get the negative message back. So if there is a negative response, then try to change the arbitration IDs and CRCs. Repeat this enough times, and until you get the right CRC, in the sense you try to read the messages, what CRC or the polynomial they use. Until that, you should keep using it. It's normally kind of a brute force. If you write the algorithm, you can try out several different possibilities of CRC. So you can find it out easily. And after this, once you get to know what is the frame and what is the arbitration ID, what is the length, what is the polynomial is being used, you can modify these messages, or you can send your own messages with the same bit length and CRC. So normally you will have the control over the ECU. So this is more of a basic or kind of introduction into what we are trying to do. Now I'll give it to my colleague Falgun, so he will take you through the demo or the setting up the demo, what all the different ECUs are used and how it is being assembled.
Thank you, Praveen. As Praveen explained, the brief introduction of why the car hacking is actually important. So now let's get into the demo setup. So before that, a general introduction of what an ECU is. ECU is just a small embedded digital computer, and then it runs in a closed control. It tries to read the data, sensor data from different sensors. It handles specific tasks, like for example, there might be engine control ECU, which handles the speed, RPM and stuff. There are typically around 80 to 100 ECUs in a modern car, and the examples of ECUs are, as you can see, body control module, powertrain control module, door control unit, engine control unit, speed control unit, transmission control unit, and ADAS, the newly coming up ADAS ECUs. Now this is how a typical car looks like. So there are various ECUs connected, and each of these ECUs will handle specific set of functionalities, and each of these ECUs are in communicating between each other using the CAN network. There will be CAN messages that get exchanged, there are also other set of messages like LIN, FlexRay, that will be specific to some of the modules, like for example the door control module. To communicate with the actual mechanical part, it uses the LIN. But majority in the car, the complete network would be connected over a CAN. This is how a CAN network looks like. It's a very minimized model of a CAN network. So there will be a main CAN bus to which all the ECUs will have connections, and whichever ECU wants to send a message, it puts the message onto the CAN bus and with a specific destination ID, and that destination ID will be programmed in different ECUs. So whichever ECU has to receive this information, so it receives this information, unpacks the information, and processes the information and takes the necessary actions. So here you can see a message that is put on the CAN bus is accessible to every ECU. So this is the main principle that we are going to use. to hack the car network. So if we get an access to the CAN bus in the car, so then a small ECU as small as a Raspberry Pi, we get the CAN messages, and then once we start deciphering the messages, we can get, as Praveen explained in the technique of hacking. So we get the CAN message, and then we try to analyze, and then we send out the correct arbitration ID and the functions. And also how a car can be hacked. There are these OBD ports, onboard diagnostic ports. So we connect to the onboard diagnostic port, and then this will be available under the steering wheel or near the bumper. So using these OBD ports, we hook up the OBD port with a connector, and then from there we can start sniffing the CAN messages like on a Linux terminal. Where you just use a CAN dump, and then you start receiving all the CAN messages. And this is the block diagram of our setup. We have 3 ECUs. One ECU is the NXP board. The other unit is the vector. We have used the vector canoe display. This is to simulate the display unit function. And the third ECU is the hacker ECU. We have chosen the Raspberry Pi, and we have added the CAN transceiver on top of that. So there is a connection between the main ECU and the NXP board and the vector canoe. The thing that we want to stress here is this replicates the small functionality of a car, and if the hacker tries to get access to the main CAN bus and gets a connection out, so he can connect that CAN bus to the hacker ECU, which is the Raspberry Pi, and then start sniffing the messages. So one thing I forgot to mention was, so in a CAN bus, there are mainly 3 wires. One is CAN high, one is CAN low, and then the third one is ground. So basically we need 3 wires to pull it out, and then connect to the small ECU, and then we should be able to read all the CAN messages. And this is a small setup that we have done, a 3-way connector to get the CAN messages out onto the Raspberry Pi. So this is the complete connected setup. The setup is here. It's due to the place constraint, we'll not be able to show. We'll show the demo on the canoe display board, but this is how the connected setup looks like. Now, so what do we do on the connected hacker ECU? So first of all, when we open a connection, we open a SSH connection onto the Raspberry Pi. We have on the Linux OS, we just open up the connection, and then we issue the command CAN dump. This command will tell us all the CAN messages that is being exchanged on the CAN bus, or rather all the CAN messages that the Raspberry Pi is able to see. So how do we interpret a CAN message here? So each of the entry is a CAN bus, and this is the network ID channel name. This is whether it is a transmitted message or a received message in terms of the connected device, which is the Raspberry Pi ECU. And this is the arbitration ID. This is the data length code, and this is the data itself. So here, as you can see, we have taken a snapshot of the CAN dump, which we connected onto the Raspberry Pi. And what we try to do is, once we start receiving the messages, we take a bulk amount of message. We start analyzing each of these messages, try to see what different messages are getting periodically exchanged between the NXP board and the vector canoe, and then try to find out which is the arbitration ID, which is really important. And then after that, we try to send the message back again using our NXP, our Raspberry Pi board. If we get a negative response code, like for example here, we send some message, and I think here, so in the demo we will show the negative response code, and then how do we send a message? It would be using a CAN send. That's another API. So using CAN send, we send out the message. The format would be the CAN channel interface name, and then next the arbitration ID. Hash is the, we give hash to differentiate between the arbitration ID and the data and the complete data that we send. So whenever we send that message, so you can see that here in the CAN dump we have captured that the Raspberry Pi is sent to transmit. That's why it's a transmit message, and then the whole message is being sent onto the network. Now we'll switch into the demo. So this is the Kenoi dashboard that we have developed. So this is a very small part of the dashboard. We are trying to, the functionality that we have implemented in our NXP board is a speedometer, the fuel tank indicator, the RPM, the left and right indicator lights, and then we have the volume control here, and then different radio station being played. We have also simulated the messages that get transmitted. So using the keyboard, whenever we press some keys, so that would simulate the message in terms of, like, for example, if the driver is pressing on the accelerator button, so we have simulated that using a key press. So like, for example, if I keep pressing the keyboard button, specific key button, then the speed keeps increasing and the speed decreases. I can switch on the indicator light, switch it off. So this is the simulation of a normal car, a small part of the simulation of the normal car that we have done. Now there is another PC that is connected here, and there is the Raspberry Pi. This is the hacker ECU that we have programmed, and then the connection is made to the Raspberry Pi, and Jay will explain here what he's going to do with the hacking ECU. So this is the terminal 3 SSH terminal that he has opened onto the Raspberry Pi. So we are logged into the Raspberry Pi, and then what he would, the action that he would be doing is try to sniff the CAN message by using a CAN dump. All the messages that are being transmitted over on the CAN bus will be displayed on the CAN dump, and then we have already analyzed the code. So he'll be trying to send CAN messages on top over the SSH connection from the Raspberry Pi to the NXP board. If there is, we also have the CRC functions implemented. So without CRC, it would give us a negative response code. And then we have brute forced, as Praveen had mentioned previously. So we had brute forced using the different polynomial function to find out what is the exact polynomial function that has been used in the NXP board. And once we get the right polynomial function using the different arbitration ID, we try to have, have written a script which will try to send out the message periodically, different important messages, like for example, in terms of speed, it keeps changing. So whatever value that is being sent from the main ECU, main car ECU, from the which is a simulated version of the driver's input, it will get masked using by the Raspberry Pi hacked commands. Just a second, we are trying to get into the Raspberry Pi SSH connection.
In the meantime, does anybody have any questions? If you have one, Praveen can take one. Yeah.
What is the arbitration ID?
What is an arbitration ID?
Okay, clauses.
So, when I send a CAN message, I have an address where I want to send the CAN message, and this is identified the address by the arbitration ID. So this includes the ID of the receiver of the CAN message, and also has a priority information from the CAN message, because the arbitration is a rule of the priority.
So my question would be, what hacker would use this way to get into a car? Because as I understood it, you have to get into the car to put the Raspberry Pi in.
Right. It's a very good question. It's a very good question because this is a scenario that is not very known at large. And the question is why, I mean, I need a physical access. Why would that happen? But that's very typical because most of the vulnerabilities that we have seen in the past, for example, the vulnerability discovered by ADAC, it was Audi TT vulnerability with an airbag disabling. That happened in the garage. So this is exactly, this OBD2 port is exactly for when you take the car to the garage for your service provider to plug in and update your software. It turns out there was a malicious software in the PC of the the service provider, and there was some malicious code in it. So it is very likely that you'll be able to do that. Now, the second scenario, imagine that you do not have any access, but still this OBD2 port is very, very vulnerable, because the development is going toward in this direction, that you can buy actually devices from the market that gives you a Bluetooth connection with your mobile device with an OBD2 port. And that's it. If you can somehow get into the OBD2 port remotely, the rest is what Falgun is showing here.
Okay.
That's why it's very important. But good question, yeah.
So you don't always need the physical access. You can also do it by remote.
You can also do it if there is a remote interface to the OBD2 port, which will be the future. You will be able to connect your mobile device with OBD2 port, and then this is the rest of the mechanism is roughly the same.
Okay.
Yeah, so to add on to Hassan's point, so the whatever Raspberry Pi unit that we are having here, so we can just make that as a hacker unit and then plug into the OBD port and then leave it in the car, and we might just add a Wi-Fi module on top of that, and then from outside anywhere you can just connect into this Wi-Fi network and then start hacking into that.
And that's how they hack the keyless go cars?
No, keyless go is using...
Keyless go was not done that way.
It was not even a hack, right? It was, explain.
It was more of, it was more of creating a kind of a message repeater. Which because normally if the key fob is in the bedroom and the car is in the garage, the distance is more. Normally this handshake doesn't happen. So they will create one more hardware device which is kind of a repeater. So it will repeat the message, amplify it, so that it makes it feel to the key fob that to the car that key fob is near, so that the handshake is happening. But this is not something physically connecting. But as I said, it's not that always you have to connect an Raspberry Pi. This is something we are showing to a car in order to get into the canvas. There are also other ways, like I show in the said in the Chrysler hack. First they got into the infotainment, then they were able to download the malicious firmware through which they are able to get into the canvas. So that is also possible. Yeah.
What is the minimum number of trials for
Okay.
Well, that is a very good question, and I think this question is minimum amount of trial to crack the CRC, right? It will depend. This is something that will depend on the length of the message and a lot of things. So the short answer is it's possible with a very simple PC. It doesn't take forever.
In a simple space you experienced?
Well, I mean, I tend not to give you an answer because this is a mathematical question. If I don't have the exact number, I would...
So again, it depends on the complexity of the crypto algorithm that you want to use. So if you're having some messages which are not crypto encrypted, not all the messages are encrypted. So if you're having some messages which are very much periodic and then not that critical, then you can literally read out the message and then just send the same message, analyze, which would take like half an hour, and then send out the message. If the algorithm is really complicated, you try out a number of times, and then one thing that you can do is take a huge amount of CAN dump and then not send to the on the network, but just try it out, different combination using a script saying that, okay, for this kind of input, what would be my CRC? And you have the calculated CRC on the message itself, the received message itself. So you try to calculate and then try to match with one message and then try repeating the same thing on the different messages. Once you make sure that you have a feeling of, okay, this might be the CRC, then probably you can try it on the real car. Sorry for the delay, we got the things back up. So now I hope you can see the font, but if not, it's just trying to do a CAN dump. So these are the messages that are getting exchanged in the CAN ECU. So if I say, if I change any of this code, so you can see different messages being exchanged here. So using this, he'll try to send a CAN message. You can see that, it is CRC protected. You cannot actually notice from here that it is CRC protected, but it is CRC protected. But once he tries to send the CAN message, Yeah, so here is the negative response code that we got for that particular arbitration ID. He tried to send it for 407, and then we got 07 and FF. That is the negative response code we got. So that's when he realizes that, okay, there is something wrong, and then he tries to use the CRC function. And then using that, he has written a script, which he'll be running. And this is the output when he runs the script. He has analyzed, and then found out the right CRC function, which will not be showing here. So after getting the right CRC function, he has written a script which will try sending different messages. So if you see, the fuel indicator is just going haywire just because of the script. He is trying to send a message every 1 second, and whatever the main ECU does, it does not matter at all in this meantime, because that signal is getting masked directly from by the hacked ECU. And this is the speed change ECU. So the speed and RPMs are getting changed randomly, even when the actual speed is different. So this is a very major security threat, because once the hacker gets access to these messages, say for example, the driver is driving the car on the highway, so he tries to see this different speed. Actually, the car might not be going at this speed, but he'll get a shock of his life that what is happening. I'm right now I'm going at 250 speed, and then suddenly changing back to 40 kilometers per hour. So this is a very security threat consequence. And also we have seen this being done on a real car. We had taken a small car dump, the can dump from the real car, and then we had analyzed. Based on that, using that functionality, we have coded a minimalistic set of functionalities on the small ECU. So now Jay will be explaining. He'll be explaining about the future scope of the project.
So right now we just implemented a minimalistic functionality, and going forward we need to prove this concept on a larger scale. So for that we need to try the UDS protocol, where we flash the software. If you're able to hack into the secure session, we'll be able to control the firmware that is being written, and also reverse engineer. As you know, the UDS is a standard protocol for the diagnostic functionality, where we have offboard diagnostics, where in a garage somebody can diagnose your vehicle for faults and errors. And so some of the major so there are different services, many of which you can use to follow a secure flash. And if somebody is gaining access into the secure session using some of these IDs that you see on the screen, it's also possible that you corrupt the firmware. But as in many cases, there is a check on the downloaded firmware before you start execution. There's a problem that there's also a possibility that this is covered in the current safety mechanisms. But what is not covered is when you try to read the memory by reading from a particular address, which in most cases can be guessed. And here you have access to the firmware, and you'll be able to reverse engineer the firmware using some reverse engineering tools like Ghidra, and this can be used to corrupt the software. So the next other option would be to use let's say an AutoSAR CAN stack, where we can prove this concept by implementing the SecOC communication and try to hack in. So this is the plan going forward, to prove this concept and to try to find out the vulnerabilities. Yeah.
So any question?
Thanks. So in the beginning, you were mentioning that you were basically forging these messages to have wrong bits set in order for I believe it was the sending entity to ultimately decide to switch off, yeah, which of course assumes some kind of fault detection ultimately.
Correct.
Did you check, or are you working with other DOS attacks, like targeted DOS attacks that actually target like counter jumps, counter overflows, or any like flooding of the CAN bus with way too many messages, or any like electrical attacks?
Electrical attacks. Well, I mean, within the scope of this project, no. I mean, we have other customers that we work on different, but within the scope of this project, it has been, like I said, the concentration was to come up with a proof of concept where we can hack an ECU, replicate the CAN messages, and a minimalistic DDoS attack. To answer your other part of the question, flooding, and have you considered much?
So not here. We're actually working on a live project for a OEM where we have this this possibility considered already. So there are safety mechanisms in place where you find that when the CAN bus is being flooded and there is no possible response, there are timeouts, there are safety mechanisms in place already. So that's something we did not consider here. So we have already experienced this possibility in the live scenario.
Okay. And like minimalistic security features like these counters, for example, that theoretically should prevent replays?
Exactly. So there are also possibilities that due to overloading of the ECU itself, the CAN stack might skip a cycle. And then we have the counters, as you said, where it checks the current counter minus with the past one, and then sees that, okay, I've missed a beat. And then depending on the criticality, we have to go into a safe state, or we have to notify the actual applications using these messages that there might be a possibility that you're working on a older message than intended.
Okay, so was getting into the safety, what was it called? Fault secure failover state of the car. Was that actually also a target? Instead of DOSing the system, forcing the car on the highway into the secure failover state?
Yes.
Okay. Thanks.
Next question.
What are possible approaches in fixing this issue with the CAN bus? Because in my opinion, you have already lost if an attacker gains access to the CAN bus. And are there currently any approaches in either fixing this with real crypto, or maybe replacing CAN bus with something completely else?
A very good question. You want to take it?
So one thing that is coming up in the AUTOSAR stack is the crypto and the IAM stack. So in the IAM identification and authentication management. So one thing what we can do right now is maybe for each of the CAN message that has to go out or that comes in, we make sure that each of the ECU is actually authenticated before saying that this has the permission to receive the CAN message itself. Not all the ECUs will receive the CAN message on the CAN bus. So that would be one possible implementation that can be done with the IAM in the crypto AUTOSAR stack.
Okay. I mean, you can make it. Here is the law that's axiomatic. If some human builds a system, you should be able to unbreak it. This is for sure. You can only make it more difficult. So the only thing, if there were a crypto on top of this CAN messages, if they're like encrypted, it would have been much more difficult to brute force. CRC is not an encryption, right? I mean, you can break it. But if there's an encryption, it's much harder. It's not impossible. It's just going to be much harder. It doesn't take much to put a little crypto.
That's right.
Maybe if I may add something here to have a bigger picture as well. Mm-hmm. There are, of course, approaches like anomaly intrusion detection for cars. So there's, interestingly, in Israel, there's a very vibrant and vital startup scene. So they're like popping up like mushrooms. Security, automotive companies.
And one of them was acquired by your company?
Yeah, thanks for mentioning that. Yeah, true. So this is, of course, attractive for many car manufacturers that there's such a focus on that. And in terms of additional or, let's say, exchanging the bus systems as such, there's also one approach, having automotive Ethernet in the future. With more bandwidth, with more possibilities also to introduce security features. And you need this bandwidth to have the support of future automotive architectures. So there's this idea of having more intelligent components in the car, capable of more than only one ECU functionality. So also this is, of course, kind of a trigger, a driver to have also introduced more security in the cars, because then you have more storage and more computing power that we need also for this crypto.
Any other remark? Rolf? Mark?
I'd only have a remark on that. So what currently other manufacturers and OEMs are doing is that they do not encrypt their messages, because in many cases you decide that you do not really care who knows what in a car, but you rather go for signing. And they do that by using HMAC and asymmetric encryption. Efficiency of which is questionable, but the problem is actually that if you do hashing, well, not hashing, but macking, for example, the messages explode in size. And the problem with CAN is that standard CAN can only transmit 8 bytes. And every byte and every bit within a byte is used differently in many of these systems. So that is also a reason for automotive CAN, because even if you decide that you do not want to encrypt, which again adds size, but only want to hash or MAC, it will explode your message length. So we're talking about factors of like 9 times the message length. And that is something that in many cases you cannot afford.
And that's why, as on the holistic approach you talked about, we have to look at the entire vehicle architecture. And we have CAN-FD, we have FlexRay. Now I think the future is moving toward Ethernet. So if there is no more questions, so I have a question to you, because this project will be ongoing, and what we see in the automotive industry today when we try to recruit, we find ID security experts. They're very good ID security experts, or very good automotive engineers. So it's really, really difficult to find a blend, who understands automotive engineering at the same time security. So those of you who are interested in doing a master's thesis, an internship, or eventually working in such field, we are actually hiring for this particular project. So feel free, we encourage you to get in touch. Even if you don't want to work, maybe join our workshops, get involved, and we will be welcome you to have you on board. Yeah, thank you so much, and big hand for the team. So the panelists, anything else to add in the end?
It was very nice, and also very interactive.
Very interactive.
I really enjoyed that.
Thank you so much.
Thanks.
Yes. Thank you very much. And I would like to add one word, maybe a magic term: trustworthiness.
Trustworthiness.
So this is something that is very important in the automotive industry for the highly automated driving. You need trust to get the passengers trust the algorithms they use. Otherwise, they won't use it. That's our experience.
Yeah, so trust your car even tomorrow. So enter your car without any worries. The probability, in fact, is not that high currently to get hacked. So I would even say that it's still in kind of, let's say, experimenting mode. There are proof of concepts. There are academic hacks. Of course, they have impact. But even if you look at the Jeep hack, is what's not the case that the week after publishing the Jeep hack, thousands of Jeeps were just crashed? No, of course
there is actually a reason for that. The reason is, the motivation of the internet criminal industry is the focus is somewhere else. Easier, more lucrative targets, like ransomware.
Yeah, good for us.
Yeah. There will be just a question of time that those will become more and more secure, hard to get into, and it's just a question of time. With economic incentive, people will get into your automotives. And there's not only economic incentive, there can be political motivation. There can be other motivations to hack into your car. It's not happening today is not because it's not possible, it's just that there's more money in somewhere else.
I don't disagree. It's just a question of time. On the other hand, if you are a manager and have to decide on budget, you are calculating with risk and benefit and costs. And as long as there's, let's say, not that criminal energy behind it, maybe besides the key fob thing. But even in that case, the calculation is like, okay, what does a new introduction of brand new key fobs, what does it cost me? And what does it cost me if 100 cars per year are stolen? Well, the insurance pays, yeah, and those guys distribute it to all of us. So there's not really, let's say, pressure currently. But I agree that this will change. That's what I want to say, that, okay, currently maybe academic proof of concepts, but this will of course change as we have seen it in other domains in the past. Well, at the end, I mean, as of course automotive security sounds very attractive, at the end I sell insurances.
It's kind of like, you know, like a deja vu coming in automotive industry. The policy enforcement point, policy decision point, the session management in identity and access management that we talked about 10 years ago, now Adaptive AutoSAR has a component for it. Because there is no way you will be able to deal with complexities like car-to-car or car-to-X communication without having a proper identity management system.
Okay, not to open the next box, I think this was supposed to be the closing words, so...
This was supposed to be the closing words, yeah. I mean, if we start identity management, I think we'll go on. But again, thank you so much for joining. Yeah, and let's be in contact. We will, if you're not yet the group member, please subscribe to the group, because we'll be announcing more events, and please join us.
And if you have topics that you're interested in, you can also share it with us.
Yeah.
Over the group chats or by email.
Absolutely, absolutely, always open. Thank you so much to the Matrickz team and Mark. Thank you so much for organizing it, and the panelists. Thank you.
Thank you.
Thank you.
In this podcast show, we bring in the industry leaders and experts in the automotive domain to share their experiences along their journey. The mission of our podcast is to start a dialogue that will allow us to understand the development of automotive industry and where the automotive industry is going. You can ask questions to our guests directly. Just send us an email to podcast@matrickz.de. We'll schedule a call with you during the recording, and you'll be part of our show. Make sure you subscribe so that you don't miss any new episodes. Please share this video to help others get enlightened as well, and that would mean a great deal to us. See you in the next episode.